The next speaker is Kaifeng Bu from Harvard. Please.
Okay. Thanks, Power, for the introduction. And also, I would like to thank Arthur and other organizers for organizing this nice conference. And today, I'm very glad to introduce our recent work on quantum circuit complexity and quantum resource. This is a joint work with Arthur and Roy Garcia, a graduate student from Harvard, and Dex Cole from Singapore, and Ruli from China, to talk about quantum circuit complexity. Let us first go back to the classical case. For classical circuit or for Boolean circuit, there are two basic gates. One is AND gate, the other is OR gate. Here, all the variables are Boolean variables, which means they take values from 0 or 1. And the AND gate will output 1 if all the variables are equal to 1, otherwise it outputs 0. And the OR gate will output 1 if there exists some variable equal to 1, otherwise it outputs 0. And the Boolean circuit is, consists of these two basic gates. And here we also allow the NOT gate at the beginning of the circuit. And for the circuit, we consider two basic quantities. One is called depth, which is defined as the number of layers in the circuit. The other is called the size, which is the total number of gates in the circuit. They basically determine the running time of the circuit, which means they quantify the complexity of the circuit. So here is an example of Boolean circuit with a depth equal to 5 and size equal to 11. Now, if we have a Boolean function, if we would like to represent it in the Boolean circuit, a natural question is how many layers and how many gates we need to express this function f. So to answer these questions, let me introduce a very, very important concept called sensitivity for the Boolean function. Here, for convenience, I changed the domain from 0, 1 to +1 and -1. So now the definition of Boolean function is from +1 -1 to the power of n to +1 -1. And the sensitivity or the inference on the ith coordinate is defined as the average value of the square of discrete derivative with respect to the uniform distribution. And if we sum them together, we will get a quantity called the total inference. And the total inference sometimes is also called the average sensitivity in the literature. Now, if we write the Boolean function in the Fourier expansion, here the base function is called the parity function, and the coefficient f at s is just the Fourier coefficient. And if we use this Fourier expansion or Fourier coefficient, then the local inference and the total inference could be rewritten by the square of the Fourier coefficient. Because we choose the function, the domain of, because the Boolean function takes value in +1 -1, so the summation of the square of Fourier coefficient is equal to 1, which means the square of Fourier coefficient define a probability distribution over all the subset of n. So the total inference is just the average of the size of subset with respect to this probability distribution. The quantities we used here has a lot of applications. For example, in the linearity testing and the learnability But here, we focus on the application of the sensitivity in the circuit complexity. There's a very classical result about the circuit complexity and the sensitivity. So if a Boolean function can be represented by a depth d, the polynomial size circuit, then the total inference of the function, a Boolean function f, and the depth of the circuit satisfy this inequality, which means that the depth of the circuit is lower bounded by the sensitivity of the function. Okay, this is a very classical result for Boolean circuit. Then the natural question is, how about quantum circuit complexity? In quantum computation, the quantum circuit is usually presented by a large unitary operator on n-qubit system. And the quantum circuit complexity is just defined as how many, the number of 2 qubits to generate the target unitary or approximated target unitary. For example, here's a big unitary on the n-qubit system, and we would like to use this small unitary gate to approximate or to generate this big unitary. So this is the definition of quantum circuit complexity. And back to 2006, Michael Nielsen and his collaborators proposed a new complexity measure called circuit cost. Here, we suppose that the unitary is generated by some time-dependent Hamiltonian according to the Schrödinger equation. And we also require the unitary at some final time is equal to the target unitary. And for each Hamiltonian H, we can decompose it into the linear combination of Pauli operators. And for this decomposition, we can separate it into 2 parts. The first term is the summation of all the Pauli operators with weight equal to 1 or 2. And the second term is the summation of all the Pauli operators with weight larger than 3, or larger than or equal to 3. And they define some cost function on the Hamiltonian, which is just the summation of the square of the Pauli coefficient, but with some punishment factor on the higher weight Pauli coefficient. And here the punishment factor P is usually very large. And for each curve from identity to the target unitary, we can define the cost function for this curve. And the circuit cost is just defined as a minimization of all the costs over all the curves. So this is just the geodesic distance from the identity to the unitary according to this metric FH. And they also show this new complexity measure, circuit cost, provide a lower bound on the circuit complexity. And the concept of circuit cost in recent years is generalized to some more fancy concept called complexity geometry by Brown and Susskind. Now the question is that, how could we, what's the circuit cost of a quantum circuit, or what's the circuit cost of a target unitary? Similar to the classical case, we also would like to define something like the sensitivity of quantum circuit. But before defining sensitivity for quantum circuit, let us define something called the sensitivity for quantum states or quantum observables. So given a quantum observable or quantum state O, we can use it to generate a probability distribution over all the Pauli operators, like this one. And recall that for the Boolean function, the local inference is defined as the summation of the square of the Fourier coefficient. So a direct analog for the quantum case is defined as the summation of the probability distribution defined by the observable, the state O. And this definition is good because it's equivalent to the Hilbert-Smith norm of the operator after the action of single qubit depolarizing channel. So it somehow quantifies the sensitivity with respect to the depolarizing channel. And then the total inference is it's just the summation of the local inference for this quantum definition of sensitivity. And we can also rewrite the total inference as the average value of the support or the size of Pauli operators with respect to the probability distribution defined by the observable state O. Okay, this definition of sensitivity or inference was originally proposed by Montanaro and Osborne back to 2010. And the reason we care about the sensitivity of quantum state or quantum observables, so we found two interesting facts about it. The first interesting we found is its connection with scrambling. Okay, scrambling measures the delocalization of quantum information by a chaotic evolution. And one widely used measure of scrambling is called OTOC, out-of-time order commutator, or out-of-time order correlator, which is defined as the Hilbert-Smith norm of the commutator between two observables OA and OD. Here, the A and the D are two subsystems of the n-qubit system. And here we take both A and the D to be a single qubit system. And for simplicity, we fix D to be the last qubit. And we take A from the remaining n-1 qubits uniformly random. And when we take the qubit for the qubit for A, we choose the observable OA to be non-identity Pauli operators with uniform distribution. For example, if we choose the A to be the first qubit, then we choose the Pauli operators, Pauli X, Pauli Y, Pauli Z, with equal probability 1/3. And then we choose the second qubit and choose Pauli X, Pauli Y, and Pauli Z, and so on and so on. And finally, we find that the average value of the OTOC is equivalent to the sensitivity of the observable OD. So this is an interesting connection between the scrambling or OTOC with sensitivity of the observables. And the second connection we found is the connection between sensitivity and magic. To talk about magic, we first needed to introduce some basic concept of some called Clifford unitary or stabilizer circuits. Clifford unitary is defined as the unitaries that map Pauli operators to Pauli operators. And this family of unitary is not universal. Not all the unitaries can be generated by Clifford unitary. In fact, it's a very small family of unitaries. And the states generated by the Clifford unitary on the 0 state is called a stabilizer state. And if we measure the stabilized state or stabilized circuit in the computational basis, then the outcome can be simulated on a classical computer efficiently. Here, efficiently means in polynomial time. So this result is known as Gottman-Kernel theorem, and it tells us that such quantum circuits do not have quantum advantage. So to get a quantum advantage, we need some quantum state beyond the stabilizer state. So we need to introduce the magical state or non-stabilizer state. So here's an example of widely used magic state which is called a T state. The reason why T state is so widely used is because it could be used to generate the T gate. And the T plus Clifford unitary is universal, which means any unitary could be generated by Clifford plus T. And this protocol to generate to realize T gate by the magic T state is called a magic state injection, which is very useful especially in the fault tolerance quantum computation. Okay, now to quantify the magic in quantum states, we need to introduce some resource measure, which means we need to use some measure to quantify how much magic it is in a given state. So for a given state, for a given pure state psi, we can define a probability distribution over all the Pauli operators according to this formula. And then we just take the entropy of this probability distribution. And we can show this is a good measure of magic. And in our paper, we call it quantum Fourier entropy. Okay, so this is the definition of a resource measure for magic. And then we show the quantum Fourier entropy or the magic measure is upbounded by the sensitivity or the total inference of the state up to a log n factor. And we call this inequality as a quantum generalization of Fourier entropy inference relation. This is quantum generalization is because there's a classical version. And back to the classical case or for Boolean function case, there's a Fourier entropy inference conjecture, which conjecture that the Fourier entropy of a Boolean function is upbounded by the total inference or the sensitivity of the Fourier function up to a universal constant factor. Universal here universal means it is independent of n. Of course, there are some recent progress on this conjecture, but it has not been proved yet. It is still open. Okay, so here are two interesting facts about the sensitivity and the scrambling and magic. But here we focus on the circuit. We want to see the application of sensitivity in quantum circuit complexity. But until now, we already defined the sensitivity for quantum states or quantum observables. Then the question is, how could we define the sensitivity for quantum circuit or for unitary? And how could we show its connection with the circuit cost of circuit complexity? Before answering these questions, let us take a look at other people's work on the connection between circuit cost and the entangling power. Entangling power is just defined as the ability of quantum circuit or unitary to generate entanglement. So for a quantum circuit, the input state could be separable state or product state, but the output state will still have entanglement. So the entanglement power is just the maximal amount of entanglement could be generated by the circuit. And in the last year, Yan's research showed that the circuit cost is lower bounded by the entangling power. And here the entangling power is quantified by the entanglement entropy. So this is some result show the connection between circuit cost and the entangling power. And back to our question, we would like to use sensitivity, or we would like to define the circuit sensitivity. So here we define the circuit sensitivity as the maximal change of total inference by the unitary or by the quantum circuit. You can simply think this as an average version of light cone. And use this definition of circuit sensitivity, we can show the circuit cost is lower bounded by the circuit sensitivity up to a universal constant. But this bound only works for shallow quantum circuit. it is very loose for if the quantum circuit is very deep. And there are more. We also have more results about the circuit sensitivity and the complexity. And let me mention briefly here. First, we modify the definition of circuit sensitivity and show the match gate are exactly the quantum gates with vanishing circuit sensitivity. And the match gate is another family of quantum circuit can be simulated on a classical computer efficiently, which means they also do not have quantum advantage. So we also need quantum gates beyond the match gates. To quantify how far a gate is away from match gate, we need to define some measure called non-Gaussian. And using the quantum entropy Fourier inference inequality, we also show the connection between magic and non-Gaussian. And we also show some lower bound of circuit caused by the magic in the circuit. And we are just starting the research on the circuit complexity, so there are still several directions or several problems we are considering now. For example, is there any better bound for the deep quantum circuit, or using magic or using circuit sensitivity? And the second thing we are considering is the classical simulation by sensitivity, which means can we bound the running time of classical simulation of quantum circuits by the amount of sensitivity? And the third thing we are considering is the sensitivity in quantum machine learning, especially its connection with the generalization error of quantum machine learning algorithm. Generalization quantifies the behavior of the learning algorithm on the data you haven't seen outside of the sample set. So this is also some problem we are considering now. And the last question is quite related to the open problem proposed by Michael Friedman on Monday's open problem session. So here we're considering how to construct a family of restrict quantum circuit with 2 to the power of n number of basic gates. So for example, we consider stabilized circuits. So by a very simple counting argument, we can show that typically to generate a stabilized state, the number of gates we need is more than 2 to the power of n. But but the question is, can we give a construct proof? Can we construct a family of such stabilized state with such exponential size? Okay, so these are some problems we are considering recently. And before the end of talk, I would like to thank Qinling Zhou and Xun Gao for the helpful discussion on the circuit complexity. And I also would like to thank TRT and ARO Muri Grant for the support. And thank you all for the attention.
Okay, any questions?
Hi, Steve Lamia. I'm curious about, can you go back a slide? I don't understand why you say Steve Lamia. Is this on? It's on. Okay.
Oh, you can use the microphone here.
No, go for it. I mean, you said something about exponential size circuits and stabilizer circuits.
Which one?
It was towards the end. I'm confused by the statement because Clifford circuits all have depth at most n squared over log n, because there's only, there's only 2 to the n squared order n squared stabilizer states.
Yeah, I think it's 2 to the power n squared number of quantum stabilizer states, right?
Right, but I guess I'm just confused by your statement because while there are an exponential number of such circuits, they all have small depth. So it seemed to me that you were trying to construct deep circuits or large circuits in some sense, but I don't think that you can do this?
Oh, no. Stabilized
Maybe can you clarify the statement that
you mean the open question?
It was the open question, yeah.
Okay. Yeah, so
exponential size, exactly.
Yeah. So like so the total number of stabilized states for n-qubit system is like 2 to the power of n square, like order n square. But for each layer, if we restrict the gates to be like C naught, T, and S gate, you have finite choice. Like you have like n finite choice to the power of n, and how many layers you need to generate like 2 to the power of n square number of gates. So the layer we need is like exponential.
Maybe this is an order of quantifiers thing, but for sure, every stabilizer state can be output with a circuit of depth n squared over log n, even if you have some restriction.
Yeah.
I mean, maybe if you had some, maybe it's slightly deeper if you have some kind of dimensionality constraint, like nearest neighbors or something.
Yes.
But I just don't think that this is possible the way that it's stated. Anyway.
Okay, we can discuss.
We can talk more later.
Yeah.
Other questions?
So, Renato Renner, I have a question about this magic or a measure of magic that you introduced. So this is defined in terms of an entropy. I guess this was von Neumann entropy of a state.
You mean the entropy for the magic?
Yes, okay. Right. So my question is how this relates to an actually, let's say, operationally relevant quantity like the number of magic states you would need to introduce, because the entropy is kind of bound, I mean, an expectation value. So does this tell me if I construct a circuit, how many of these states I would actually need to inject? Is there a relation between that measure and yeah, that kind of requirement of resources in a sense?
You mean how to use this entropy measure to give a lower bound of how many T gates you need to generate a target unit?
Maybe my question is more about, yes, in a sense, the operational meaning of that measure.
Oh,
so why do you define it in that way? What does it tell me really?
Oh, yeah. So first we start, we define, we first consider, not consider the entropy, we consider linear entropy. We consider zero entropy, just the rank. You can write the pure state, any pure state in the linear combination of Pauli operators. And for stabilized state, the decomposition is very easy because you will have 2 to the power of n number of Pauli operators in the decomposition. This is if and only if condition. And if you are larger than this number, so it is a magic. This is also if and only if condition.
So it's the entropy of order 0, which is basically the rank. That
yeah, because we consider like linear entropy, and this is just a special case, like the linear of parameter tends to 1, right? And when the linear parameter, the parameter in the linear entropy tends to 0, this is the rank, and we can use the rank to bound the classical simulation time.
Okay. Yes.
Yes. So this is one application or what is that operational meaning of this kind of measure, like in classical simulation of quantum circuit.
Okay, thank you.
Yeah.
Other questions?
Since the transformation from the canonical basis to the Pauli basis is Fourier, is there a connection with your bound and the uncertainty principle?
Oh, yes. There's a very simple proof to show this kind of entropy measure is a magic measure using the uncertainty principle for pure state. Because a typical uncertainty principle for entropy is like the entropy of the pure state, entropy of a quantum state in the spectrum in its like eigenvalue decomposition, and the entropy of the probability distribution defined in the Pauli decomposition the sum of these two entropy is larger than or equal to the dimension because here we consider pure state. So the entropy of the pure state is always 0. So it gives us a low bound for all the entropy. And you just proved the equality for the uncertainty principle is if and only if the state is a stabilized state, which is the by projection in both space.
The by projection minimizes the
Yes.
Yeah,
Okay.
I hope to have a question. So when you say there is a connection between the OTalk and the magic, and is that means that when the system is chaotic enough, it has the high quantum advantage compared to like not chaotic case?
I'm not quite sure about this statement because here we only show this measure equivalent in the average case, but we don't show like the OTalk is like exponentially decaying if when the unitary is magic. We haven't done this statement. We just show the equivalence of these two measures.
So the OTalk will measure how chaotic the system is. So why you say they cannot be just equivalent?
But I think to quantify scrambling, we care about the rate of decaying of the OTalk. But here we only show like this measure are equivalent.
Okay. Other questions? All right, so let's thank the speaker again.